So it's another several days off because we had another break. The last thing that we wrote on the board was more technical than I think anybody had anticipated it being when we started. I figured, oh, I'll just rattle this out of the book because it looks like a paragraph. And it turned out to be kind of complicated. That value of PE is rooted in what it represents. So the question that we did on the board said, how much iron gets oxidized when this other thing happens, and make sure that all of the electrons you're counting come from this other thing. So there were three things happening. And each one of those three things was its own redox reaction. Now, environmental science does redox reactions a little bit differently than chemistry does it, because it wants to make the number of electrons per reaction be 1. In chemistry, we allow the number of electrons in a redox reaction to be whatever number it feels like, as long as we have a whole number of atoms in our balanced equations. And then the Nernst equation, or whatever it is that we're dealing with, just siphons off the number of electrons, and we don't worry about it. Okay, now, every redox reaction that we do in general chemistry has two components to it. The thing being oxidized and the thing being reduced. Mm-hmm. And both of those entities have values associated with the potential. There's an oxidation potential and there's a reduction potential. And because we don't want two tables full of those are numbers that are cataloged, that have been experimentally found for hundreds of years, at least 100 years. They're all in the appendix of the textbook. Okay. But they're all written down as reduction potentials. And so they're always written as entity plus electrons becomes its reduced state. And then there is a one-sided electrode potential written as a reduction potential in volts associated with that. If you want to know what the potential for the cell is of when I do a redox reaction, something shuffles electrons to the other thing. Oxidation is the loss of electrons. The thing being oxidized gives its electrons to the thing being reduced. If I want to know what the potential for that overall reaction is, we call it, in general chemistry, we call that the cell potential. It's just those two numbers, it's just the difference between the two reduction potentials of the things that you're looking at, one at the cathode, one at the anode. Okay, that's what PE is. It's the log of that. So these are numbers that are not desperately hard to find. They're all cataloged. And so when the book said, this reaction has a PE of this value, and this reaction has a PE of this value, we went, okay. That is rooted in what its cell potential is. Environmental chemists don't use cell potential by name. They call it something else. And I can't remember what that is. And we could go back in the book and check. But if I wanted to write this out as a 2 or 3 page homework question from beginning, like ab initio, if you'd like, of the electrons move from here to there, in this environment at this pH, we could make this a multi-page question, okay, which I still might do. All right, moving on. The next chapter up is descriptive. There's nothing quantitative in here that I can see. It's just descriptive. Let's talk about pure water, purification of water. All right. And that got me thinking, I wonder where our nearest water purification plant is, and it turns out it's just at the traffic light down the street. And they had a tour of their facilities last week, and we missed it. And there's not going to be another one now because it's the end of the term. Stuff happens. Never mind. Future generations of Concordia students will go on the tour. And beyond that, I was thinking, do you ever buy bottled water from the... okay, so that's the wrong question. Because
I mean, road trips, I buy a bottle of water.
not bottled water, but the purified water that's dispensed at the supermarket into your own jug. If you bring your own jug.
Oh, yeah.
They used to all be in those 5-gallon, actually there's a really good place to talk, because the chapter after this talks about organic chemicals in the environment. And one of the problems with bottled water is the plasticizer. Okay, so we don't want to make the bottles, if we made the bottles the same way that we used to make bottles be plastic, that's a lot of mass. And now I'm throwing away a huge amount of mass because the general public think that drinking bottled water is good and that drinking tap water is bad. The freshmen that I had an interaction with in the fall, I don't think that a single one of them in class drank tap water. I don't think there was a single one of them left. And they were like, ooh, you really drink tap water? Like, yep. Yep. Yeah. Yeah. But you can buy your own jug. So the little squishy bottles have been made with the minimum amount of plastic in them. And later on, we're going to find out that that is polyethylene, or polyethylene. Ethene is the common chemistry name for a molecule with 2 carbons and a double bond between them, and we polymerize that up. But the old name, the industrial name, is ethylene. So polyethylene, and polyethylene comes in a number of different varieties based on its density. Low density is like plastic bags. High density is the stuff of implants. If you're going to have a surgical hip replacement, you'll use high density polyethylene as
Most of your shampoo bottles are HDPE.
Okay.
Yeah, I've noticed it recently, and I see it. They all have HDPE.
Mm-hmm.
So.
Yeah. And so the drinking water bottles is going to be really thin, somewhere in the medium to high range. The lower the density, the flimsier the material, the more filmy it gets. The higher density it is, the more resilient it becomes. And good for the industry. They've made their plastic bottles use much less plastic, but they're squishy. And there are plasticizers in there which are low molecular mass molecules that sit in between the fibers of the polymer. And they stop it from going brittle so that the bottle can last. Now the lifespan of a polyethylene bottle was never envisaged to be as long as it currently is in the consumer marketplace, because they were developed to hold milk. And milk, I don't know how this has happened. I'm a chemist, I should know this. Milk used to have a shelf life of like 2 days. I lived in an environment where milk was delivered to your house in the morning, and the birds would pick up in glass bottles with a foil lid, and the birds would pick holes in the foil to drink the cream out of the top of the bottles if you didn't get to the doorstep in time. And you put your empties out and they were recycled. And then apparently that wasn't a good market idea.
Ultra pasteurization, is that what changes it? It's because it's like ultra, I think all milk.
So they've thrown in a couple of new techniques of not having the fat. The fat no longer rises to the top in milk. It used to. So if you had a pint bottle of milk on your doorstep, the top part of the bottle, there was a little layer of cream where the fatty content, because it's less dense than the water content, would rise. Now, milk is an emulsion. Actually, there's a couple of words that we should probably know. One is emulsion, and one is colloid, and they're kind of related to one another. It's down to, I think, particle size of what we're talking about. So mixtures are two or more components occupying the same space but not interacting chemically. A suspension is when one of those particles is not soluble enough to remain in solution, but is not dense enough, or it hasn't aggregated to a particle size that makes it massive enough to precipitate. And so it hangs in solution. The deal with suspensions is, if you give them enough time, they probably settle. And we're going to be talking quite a bit about calcium carbonate, and calcium carbonate does that. It will precipitate over time, but before it does, you get these little tiny particles of calcium carbonate, and they don't want to be soluble in the water, but the water is moving or it's agitated in some way, and it just remains suspended. A emulsion is when it's not the solute part of the equation is not a solid. It's oily liquid, and oily liquids are non-polar. Water, of course, is very powerfully polar, and those two things don't mix. So given enough time, you would think that the oil and the water would separate, but because the particle size is so small, they don't separate. So the fatty content in milk is suspended evenly throughout the milk. But it didn't used to be. So what they've done is they've homogenized the milk. Something they've removed from the labels.
It used to be on the.
Yeah.
I
Yeah.
remember seeing.
So I first came to the United States in 1992, and all of the milk cartons had the same 4 letters striped across the top of them. HOMO, HOMO, meaning homogenized process, that all the fat particles, they were strained so that all the fat particles were the same and that it wouldn't separate them, that the cream wouldn't rise to the top because people found that to be unpleasant.
Coconut milk does that.
Okay.
Sorry, I just thought.
Yeah. Well, they don't say that anymore. I don't know when it went away exactly, but somebody probably saw the joke in it and just figured, well, let's not have that word be there. So it's not there anymore. It's probably on the label somewhere. Anyway, they've managed to make, what's the shelf life of a carton of milk now?
It's all at a month.
It
Over
could
a
be
month?
about a month,
Yeah.
which from somebody my age is like, wow, that's not what my understanding of how milk used to work.
I don't know. Used to-
So ultra heat treating changes the flavor of milk. Pasteurization is a flash heat treatment which kills or stuns some of the bacteria that sours the milk, or worse, curdles them and gives you some kind of intestinal distress. But yeah, the plastic bottles were developed for milk, let's say at a maximum, it's a month on the shelf. That gives the plasticizers and the microplastic and all of that 1 month to get into the content, the food contents that you're looking at. Now, what's the shelf life of a bottle of water?
A couple years, I think, typically. I mean, if it has an expiration date.
Could it conceivably have been on a shelf in a gas station for 4 or 5 years? Yeah. Or in somebody's pantry.
Or in their car.
Yeah. For all of those years. And so there are a number of plasticizers, the softening byproducts of the process. And there's one input in particular that we want to be really, really careful with. It's called bisphenol A. It's a very early form of plastic. We don't want that in our food. It's getting in there. Okay. So the plastic bottles that you take to the store to refill, those are hard plastic bottles, the ones that are outside Amanda's office. When you bump those into each other, they clang because they're hard. Polyethylene bottles don't do that. They just thud. Those are polycarbonate. And polycarbonate, when you first buy the bottle, you can smell some plasticizer in it. So I usually rinse that one. But then they don't leach to nearly the same degree. And you can throw them around and bang them around. But when they break, they fracture. And if you ever dropped a 5-gallon, or put it down too hard in your driveway, and everything comes out. They make them in 3-gallon now, which is better than 5. Combined from HEB whenever they have them. And since COVID, it's been harder to find them. But a 3-gallon reusable polycarbonate bottle is a lot easier to pick up and move than a 5-gallon one. A lot. Okay, so when you go to the refill station, this is when I said if you drink bottled water, what I meant was the refillable one. It will tell you what the stages of the water purification at that station are. And that's on top of what the municipal supply that feeds into the store is. So, you were saying earlier, TLAP.
To the Texas Lands and something, wasn't it?
Yeah, we
It's in
should.
our email. It's
Yeah,
in the
we
email.
should all know.
I should know this for sure.
At every,
Texas land application permits is,
okay,
they're the ones who run, or like, they're the facilities or whatever, I think.
at every kind of municipal level, everywhere in the United States, there is somebody who oversees water quality in the municipal supply. That if the city is going to pipe running water to your house or your business, it needs to meet a minimum standard. And of course, if you don't have city water, I've lived in a house that didn't have city water before, have your own well, then nobody cares. Like, nobody at all cares. You have to be in control of your own quality control process. Okay, so let's look at a couple of things that municipalities do in order to have the water be clean and safe. All right, well, first of all, where on earth is this water coming from?
Aquifers?
Yeah, so what on earth is an aquifer?
It's underground, it's water that comes from underneath, below ground, right?
Yeah.
It's underground springs.
Yeah, so me not coming from an environment where we have those, this was a word that was completely new to me when I moved here 30-something years ago. And that we were at all costs to protect the aquifer. I used to live in San Antonio and we were talking about the Edwards Aquifer. And it is a massive underground system of water capture. To say that it's a cave filled with water is incorrect, but it might as well be. All right, well, where does that water come from?
The rain?
Yeah. So at all points, water is in a cycle. We have water in lakes and in rivers that is fresh water. We have water in oceans, which is salt water, which is not drinkable. But everything evaporates, goes into the sky, is water vapor, and then droplet size, and we saw changes in temperature and pressure, will determine at what point that water returns to the earth as rain. Okay. All right, so the rain comes and then it goes in a lake, and if you can siphon from the lake, then you've got lake water that will then be purified. Or if I can build a dam, I can turn that lake into a reservoir and use that reliable amount of water to feed into a municipality. Here, because it's hot so long for so many months in the year, surface water goes up and goes down. And because we're in limestone, which is porous, we have an underground water source that the water has settled, and we have an underground water source that we need to protect. Okay, so our particular water source, let's talk about ours. We pump it out of the ground. What should we probably be cautious about? You want to drink the water straight out of the ground? No. We should probably do a couple of things to it.
Well, we have to be careful for like bacteria, microorganisms to start, bigger, and then working down, metals, I guess, would be, right? You want to make sure there's no
So there's an awful lot of metal on the planet,
Mhm.
and to some degree, metal salts are soluble in water. Some of them are very soluble in water. The ones that are really, really soluble in water, we don't really worry about. The sodium chlorides and the potassium nitrates and nitrates.
Mhm.
We're not concerned too much of that. But like, hey, salt water is full of sodium chloride.
Mhm.
We can't drink that though, because once you get your salinity, your amount of sodium chloride gets to a point, the osmosis effect that it has on your biology is not good. I don't know at what point we're going to pull osmosis out of the hat and write it on the board and talk about osmolarity and possibly osmotic pressure. But it's shown up a couple of times of like, hey, there's a potential to talk about osmosis here. And because one of the processes that we're going to talk about in this chapter is reverse osmosis to get the
Mhm.
water pure, yeah, we probably should.
Yeah, that's
Okay. So even the best, so I used to have a well on my property and we used to drink well water, which is why we drink water out of the big plastic bottles that we got from Walmart with refilling the water. So we would cook and bathe
Mhm.
in the well water, but we wouldn't drink it.
Did you have a softener for your well?
Yeah,
Okay, I was gonna say, I mean, I can't imagine being able to
yeah, I had
survive
a
without it.
big to-do 2-tank water softener just to save the pipes in the house from clogging up. And then my neighbor also had a reverse osmosis under the sink, but the water pressure wasn't particularly high, and I didn't do that. We just drank the reverse osmosis water in the 5-gallon jugs that we got from the supermarket. Okay, so the water, when it comes out of the ground, potentially has several problems. So the first thing that came out that comes as the well water enters your house, the very, very first thing that you do is you filter it. We had a whole house filter, which was just a fiber. The inside of the filter was a little bit like paper.
Mhm.
I couldn't tell you exactly what the material is, but it's kind of paper-like and multiply fluted and porous. And after about 2 months, your water pressure would start to dip because the red clay that I lived in, that was the soil where I lived at that time, would clog the filter. And that was what the filter's purpose was. It was to not allow the sediment to get through. So you need a filter of some description. If you're filtering for a house, you want a filter this big, and the water just runs through it, and it's engineered to be a specific shape with a specific porosity to catch particles of particular size and let the smaller ones through. Okay, but what if I'm doing it for a town? What do I filter the entire town's worth of water through? And they're using hundreds of thousands of liters of it all the time. That's the simplest thing.
Just create, I mean, just have a massive filter where, I don't know, cook it.
What if this technology was Roman? That there was no paper filter.
You put it through like gravel, or like you'd have some sort of potential like stone rock
Yeah.
is some sort of
Sand.
sand. Okay, sand, yeah.
Sand.
Oh, okay, that's right.
So there's yeah, you just let the water run through sand, and the sand has really kind of strange properties. You've had physics, right? Yeah. You know how an hourglass, what an hourglass does? You know what an hourglass is,
No,
right?
yeah, I was trying to think, maybe creates like a choke point.
Yeah.
Yeah.
And then like one granule drips through at a time. And the flow is constant.
Mm-hmm.
And it doesn't matter how much you have in the top ampule,
Mm-hmm.
the flow is constant.
Yeah, that's not normal.
If you filled an hourglass with water and you flipped it up, the mass, the weight, would make the water run through really quickly, and then as more water drained through, there would be less mass making less force,
Mm-hmm.
and it would slow down. But granules of sand, you could make one with salt, as long as the granules are the same size.
Mm-hmm.
They just get their elbows out.
I was gonna, is it the
And there's
texture
enough
of the shape?
space. Yeah. They put enough space around them each other that they're fluid, but not interacting. There's no attractive forces between them at all, and that's why they go through like one at a time. They're like zero order. They just go through at the pace.
Mm-hmm.
It's like that. Hey, that really is zero order. You change the amount, does not change the process at all. Yeah. So if I have granules, we could start at the gravel layer. In fact, if I was good, I don't know. I've never designed one. We were talking a little bit earlier about I did visit a water treatment plant, but it was a long, long time ago. If you pass through gravel, it would pick up the big objects, like, hey, somebody discarded a bottle,
Mm-hmm.
somebody discarded a Ford Transit, somebody discarded a wheel. Gravel catches that, and then I could feed that into a sand trap. And sand comes in different levels of grit level, and over the course, if I could siphon out of one pit into another pit, I could terrace them.
Mm-hmm.
If I had, yeah, if I was Roman, I would have the water flow into a top terrace that I filled with gravel or something, and then have the water leach out of that and funnel into a sand one, and then perhaps into a finer sand at the end. And it would come out, and it wouldn't have any particles in it.
Mm-hmm.
Wouldn't have particulate matter in it at all, because the sand does sand things and just traps
Mm-hmm.
whatever. And would I bother about cleaning that trap? I don't think I probably would. You might have to fish something big out of
Yeah.
it from time to time, but I think it's probably all right. Okay. The other thing that happens is it tastes bad and smells bad. The water that comes out of the ground at the well level is not pleasant. All right, if I'm doing that for a city, what am I going to do?
Then you're gonna want to, the reason it smells is because of those little different ions that are in it, right? Like,
Yeah, it could be ionic. If it's ionic, it's probably soluble in water.
okay.
Um, if it's smelly, it's probably something small and covalent, something organic that has, it's one of those smells of deterioration that biology gives off when dead stuff is around.
Mm-hmm. Yeah.
Okay, and there are a couple of things that are culprits. Amines don't smell good, but molecules with sulfur in them,
I was gonna sulfur.
yeah, they have that. At best, it smells like bad eggs. At worst, it smells like poop. And there's all sorts of different gradations in between. All right. How are we going to get rid of the smell? Smell dash taste.
Do something to get the sulfur mixture or the.
Yeah, so there's a couple of simplish things to do.
I know the answer to this too. I was just reading about it because they do it for desalinization. They need to do
Okay.
it for. They use it. It's one of the final steps is removing the sulfur.
Okay. So if we did go and visit, which we didn't, blame that on me. I did that wrong. One of the things that we would have seen would have been these big round beds where the water comes in and gets filtered and goes out. But it doesn't just like trickle in one end and trickle out the other end. Like I would say, hey, I would build a Roman terrace and put different levels of grit sand and purify my water like that. No, they spray it in. They sprinkle it in. And Henry's Law. If you want a gas to be soluble, so if it smells, it has the potential to have a vapor pressure. If you want something with a vapor pressure to dissolve in your liquid, then you up the vapor pressure of that smelly molecule. All right. Well, what if I upped the availability of air? And air is 78% nitrogen, which has no metabolic imprint at all. Triple bond between two nitrogens might as well be unbreakable. Only nitrogen fixation bacteria break it. But oxygen, the other 21% of the Earth's atmosphere, is oxidizing. And if I spray my water around a bit, then I up the solubility of oxygen in the water. And a smelly sulfurous or smelly amine molecule now gets oxidized. And its oxidation products don't smell as bad. And then they decompose to sulfur dioxides, nitrogen dioxides, or whatever. And they stop being simple covalent molecules and they start becoming, there's a pathway for them to be small gases and for them to be ions, which will then fritter away somewhere else. Okay. So a simple way of removing a large amount of the distaste and bad smell is to aerate the water. And you can do that just like with rotating hoses, like sprinklers. The problem with sprinklers in a hot state, like Texas, is how much of that water are you now evaporating? Didn't we want to keep that water? Yeah.
So can you do jets and
I'm sure someone has engineered the most efficient way of doing it. I don't know what the best solution is, but yeah, you have the potential of losing to evaporation. And then the other magic chemical answer, which is in the when you go to the kiosk and you dispense water, is activated charcoal.
Mm-hmm. Yeah,
Have you any idea what activated charcoal is?
just carbon, right?
It's carbon.
It's like super concentrated. Wait, trying to figure out how to word that. Just a bunch of carbon.
It is. It's exclusively carbon.
Mm-hmm.
Yeah, charcoal is largely graphite-like. It is high composition carbon, and we haven't done this in lab, but in organic chemistry, actually Daniel could do this right now with the stuff that he's doing in lab. He's making his project is making all of these smelly chemicals, all these esters, and the process that he's making them requires heat, and so some of them are coming out discolored. They're all supposed to be the same-ish shade of colorless, or perhaps a tinge of yellow. But some of them look like they're red and black-ish or inky purple, and some of them are yellow, and some of them are completely colorless. If we threw activated charcoal at them, I bet you we could pull all the impurities that are causing that color out, and then he would filter the charcoal away, and we would have decolorized the material. How on earth does that work? Charcoal is this magic thing that takes away smells and flavors that we don't want.
Is it probably bonding or?
It's all on the surface. It's a surface phenomenon. It just accelerates. Things stick to it.
Yeah. Okay.
Which means that it doesn't last forever. So if I had, hey, I'm a Roman person, and I have pulled all of the sediment out of my town's drinking water, but I've discovered that if you throw the clinkers, the big chunks of coal from the fire, from a hot fire, into the last sand trap, that the water now tastes better, smells better, because the carbon is taking this out, then I could have even better water than before. But that won't last forever, because if I'm binding things to the surface, by adsorbing them to my charcoal, then that charcoal has a lifespan.
There's only so much surface for
Yeah.
each particle.
Yeah. And so charcoal needs to be replaced. I'm sure you can regenerate it. You just stick it in. I think you could probably just stick it in an oven. And that, but the downside would be it then
And you're
releases
putting your
all
smell.
of the stuff that, yeah, but what you do is you have it in this environment. You have the smell in this environment, the color, the smell, the taste that you don't want in your environment. And then you take it away and you burn it in somebody else's environment. You take it outside the environment and you release it over there. Yeah, it will find its way back.
Brita uses it. They have charcoal component to it.
Who?
Brita.
Oh, yeah.
Yeah, Brita.
Yeah.
I have a Brita at home, and it's like you can actually see some of the charcoal that they have in it.
So they have a number of different types of filter. Some of them are just regular filters,
Yeah.
and then other ones are the filters with the activated charcoal, and you pay a
Yep.
little bit extra for. Yeah, we've got those, and we've got a fridge that has a filter in it for the
You can
drinking
also
water.
give it to your dog if it gets into something bad. You can give them activated charcoal.
There are activated charcoal doggy treats. That's absolutely right, and it makes your dog's bottom not smell, apparently, as bad.
Oh my gosh,
As it
that's
could.
so funny. I didn't even think about that.
Yeah, there are dog biscuits that are that contain activated charcoal, and the dogs can eat. We've had dogs that have eaten them. I don't know how effective they actually were, because a stinky dog is a stinky dog. All right, we're almost there. What else this water needs to be good enough for me to put in plastic bottles and sell to idiots. Okay. Currently, it doesn't have any sediment in it because we've removed it by filtration. It doesn't have any odors and smells because of aeration and charcoal. Oh, the very first thing that you said, we haven't addressed. It's got somebody's E. coli. And did the filtering stop the E. coli? No. Did the air bubbles stop the E. coli? No. Did the charcoal stop the E. coli? I'm not sure. I think it might. We'll have to look that one up. I think the charcoal might be powerful enough to do something like that.
I think it does.
All right. Let's assume that it doesn't. What else are you going to do?
Throw
Yeah.
chemicals at it. I mean that's the best. I think that's the best answer.
So
right?
there are two answers here. One is actually there's kind of three. One is a chemical answer. If you run your tap water at home and you smell the tap water, does it smell of anything?
Like sometimes it'll taste or smell kind of like not metally, but I guess like almost like chlorine-ish. Yeah. So
All right, magic word, chlorine. Where has the chlorine come from?
I'm assuming they're treating it with some sort of well, chloride.
How
I
much
guess.
chlorine is in natural products?
We have sodium chloride, so there's
Yeah.
I mean it's just about everywhere. Or it's in a lot of places.
But not as so
Not as chlorine as
chlorine, group 7, has 1, 2, 3, 4. We start pairing them up. 5, 6, 7. Makes one bond. It's got one unpaired electron. So chlorine, the molecule, is two chlorines stuck together. It's a poisonous green, heavier than air gas. So when Fritz Haber developed this as a chemical weapon in the First World War, the thought was the Germans would lob the bombs with chlorine in them. You didn't have to get it into the Allied trenches, you just needed to get it close to the trenches, because the chlorine is heavier than air, it would fall into the trench. And when people breathe the chlorine in, plus water, you end up making hydrochloric acid in your lungs, which scars the inside of your lungs, which causes them to not really bleed, but to emit liquid. And then you drown
Mm-hmm.
in your own fluid. Okay. Yeah, we outlawed this. Plus, it wasn't particularly effective because when the wind would blow, the poison gas would blow back into the face of the people who used the weapon. All right. Well, the things that we see in organic chemistry is if I tie a chlorine to a carbon, we even keep a separate waste bottle for this.
Mm-hmm.
We have regular organic waste and then we have chlorinated waste because this is more harmful to the environment than just the regular organic waste. Chlorines, as covalent chlorines in the environment, tend to be antimicrobial. Which, okay, well that's not bad. I want my microbes dead. But do you want all microbes dead? Because you end up killing all the microbes that the little tiny organisms, the little fleas, the water fleas, eat in order to survive. And then who eats the water fleas? The fish. And then who eats the fish? The bigger fish. And then who eats the big fish?
Animals and us.
Birds and bears. And then who eats the bears? Yeah, well, yeah, okay. When you just blanket antimicrobial, you have a knock-on effect several generations down the food chain. Okay, so when you say you smell the chlorine, and when people say, oh, this water has been chlorinated to kill the microbes in it, they don't mean this. For reasons that have never been explained, people say, oh, the swimming pool is chlorinated.
Mm-hmm.
No, it's not.
No.
It's not. It's not. It's, well, that word, it's an improper use of the word, but that word has now become to mean something else. The molecule in question is this molecule. This is sodium hypochlorite. Sodium is in group 1, as a +1 ion. Oxygen is in group 6. It's a 2- ion, and then it is covalently bonded to one chlorine, which only leaves it a 1 negative to play with. So I have an ionic salt that's a sodium salt. What do we know about sodium salts? They're guaranteed to be soluble in water. So this is highly soluble in water, and it smells, that smell of chlorine is this. And this particular molecule is well known for its antimicrobial activity, and it goes by the nickname a small amount of bleach kills lots and lots and lots of microbes. Lots of microbes. So, yeah, if you toss in a pellet or two of hypochlorite, you're going to kill the microbes. Other ways of doing it or killing the stubborn ones that are left over.
Ozone,
Yeah,
right?
yeah. So you can
Ozonolysis,
you
yeah.
can you can undergo ozonolysis. You can ozonize the solution. Same thing. Ozone, lots of oxygen, and it has a loose oxygen that
Right.
it wants to find electrons to play with. Kind of the same thing here. That this would rather not be an oxygen and a chlorine stuck together. This would rather be a chlorine and a chlorine and an oxygen, and they'll find a way to do something else. The degradation pathway for this is water soluble. It's dilute, 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 dilute. But again, it is so incredibly good at being antimicrobial that yeah, you're going to need to dilute. Other pathways, and if you look at the kiosk that sells you the bottled water, it'll say the water goes through this many stages of filtration. It might go through ozonolysis because they don't want to bleach the water. They don't want to add a chemical to your water,
Yeah.
blowing ozone through it. Okay, it's gone because it's a gas. But the other thing that they'll do is the same as letting my water be out and having strong sunlight shine on it.
Oh, is it UV?
Ultraviolet.
Oh, right, yeah, of course, yeah.
Ultraviolet kicks in enough energy to promote an electron from a ground state to an excited state enough to go, oh, I can zap something now that wasn't within my reach before. So UV treatment, strong sunlight, or UV. The little water dispensing kiosk gets rid of, will hit with UV. I'm not sure how much you've got. While it's traveling, as the water is traveling through the pipe, the UV has to come in. Of course, UV can't go through glass. Glass
Yeah.
blocks all UV. So I'm hoping they have some little quartz crystal in there that is a window that will allow the ultraviolet to get in and zap the microbes as they travel, or any small molecule that could cause the distaste. All right, and then that basically just leaves my water is good enough to bathe in now, but not good enough to drink. And in fact, it's not really good at bathing in it because my soap doesn't work.
Yeah, it's hardness. It's
Because it's got so many dissolved metals in it. It's got the big two for hardness are
calcium
calcium,
and iron? Wait, no. Oh wait, I don't know.
magnesium.
Magnesium.
Calcium and magnesium are total hardness, and then you can have specific hardnesses
Right.
for the calcium. Usually just the calcium, you know, because you did all the work. We usually count a general, a calcium hardness number, and then a total hardness number that is the calcium and the magnesium combined. And they're
Based off of
grouped.
total alkalinity or based off
Yeah,
alkalinity and stuff.
yeah. They're group 2 metals, and depending on what they're associated with, if they're chlorides or something like that, their solubility is high. But if they're carbonates or hydroxides, then their solubility is low. And that filmy, waiting to precipitate over a long time frame is just not what the consumer is looking for. Plus, a small amount of material that is in the water that is ultimately going to precipitate as a rock is not what you want inside your washing machine, inside the pipes that are inside your house. So you want the water to be soft when it comes to your house, and if it's not, you need your own water softener in your house. So to get the ions, the metal ions out, we need to do a little bit of adjustment. There's a couple of things that will take care of that. The other dissolved metal ion of, and we can have the calcium and the magnesium become not a problem anymore with the water softener. All right, how does that work?
I actually, I used to know this, I don't remember. Don't they run like some sort of sodium bicarbonate, or wait, what, I'm trying to remember, like something like that,
They're
right?
called, they're prills. They're little pieces of salt this big,
Yeah.
which is sodium chloride.
Okay, oh yeah.
So what you do is you up the concentration of something that is very, very soluble. So you up the ionic content in a tank, and then when it mixes with the magnesium and the calcium, they exchange places, and you just overpower the amount of magnesium and calcium that's in your water supply by replacing it with the salt that's much better at doing the job than they are. Calcium carbonate. The calcium and the carbonate are two separate entities. When they come together, they're in equilibrium with calcium carbonate, the solid. Well, what I need to do is get those two to be separated from each other. So if I throw in masses of sodium, I'm going to do it a different shape. Here's sodium carbonate, spectacularly soluble in water. And so now I'm going to drive that one just down the pipes and separate the calciums and the carbonates so that they don't come together and sediment.
Okay. Oh, yeah.
It's simple. It's simple because it's cheap. And a little bit of salt in drinking water is fine. In fact, if you read all of the labels of all of the drinking waters, it will tell you where it's bottled, what it contains, has it been fluoridated or chlorinated for your safety, and has it been filtered, and then it will tell you, and we added salt because it's a flavor enhancer, it just makes it taste better. Yeah, so the salt is just to be more ionic than the calcium is, and keep the carbonates and the calciums apart from each other. All right, and then there's one last thing. Iron. There is a significant amount of iron in the soil, and as water runs through the soil into the pipes in order to be collected, it dissolves. Now, iron exists in two major ionic states, oxidation states. Iron 2 plus and iron 3 plus. Two plus is a very abundant and achievable oxidation state. For those of us playing at home, iron is 4s2 3d5. Is that right? Ooh. It's not 5, is it? It's 6.
I think it's 6.
1, 2, 3, 4, 5, 6, yeah. 4 is 2, 3d6. Yeah, manganese is 5. And so to lose the 2 electrons from the 4s shell is incredibly easy to do. So the 2 plus ion gets made very, very simply. But the 3 plus ion is more stable because this would be 4s0 3d5. And 3d5 is special because it's a half-filled shell. 3d6 has Pauli's pairing repulsions to deal with. 5 individual electrons in 5 individual d orbitals has the extra stability of those electrons not interacting with each other. All right. This one's less soluble than that one. So all I have to do is make this precipitate. And this is an oxidation pathway right here. The simple act of bubbling the oxygen through or sprinkling air into it might be enough to turn your iron oxides, iron 2 oxides, into iron 3 oxides. Iron oxides in solution are complicated. I don't know whether we did this in organic chemistry with you or not. But the hydroxide oxides and iron 3 hydroxide is definitely not soluble. So we've probably taken care of the iron, and the iron will stain your water. It will give it an unpleasant looking color. Yeah, rust, because iron 3 is the rust part. And a bad taste, and we want it gone. And it turns out that the other things that we're doing to make the water be palatable probably get rid of the iron anyway. Okay?
Yeah.
All right, when we revisit, we'll talk about something else.